Hello everybody, myself Jyoti and today's topic is quark model. This is the ninth lecture in the series elementary particles. Okay, so what is quark? We know that quark is a type of elementary particle and it is a fundamental constituent of matter. Now, when we talk about quark, these quarks they combine and they form a composite particle, and those composite particles are called as hadrons. So, when we have studied the elementary particles first lecture, like that classification of elementary particles, that time we have studied that what are hadrons. Hadrons are basically when we combine kaons, pions, and baryons together. That group they are strongly interacting. That group is the group of particles which are strongly interacting, and they are known as hadrons. And now the when we talk about hadrons, the protons and neutrons, they are also hadrons, and they are the most stable hadrons. Now all commonly observable matter, it is composed of up quark, down quark, and electrons. Now see, this is a quark. Now here, if you look at this diagram carefully, this is the example of proton. So proton, basically it is made up of three quarks. So here you can see I have U, then again U, and then D. So we have basically six flavors of quarks. So where U stands for up quark, D stands for down quark, and proton, it is made up of three quarks, up and down, and each quark it has a different color. So red color, blue color, and green color, that we are going to see later on. Okay, now why we study quark, or what is so special about quarks? So when we talk about quarks, they are the only elementary particles in the standard model of particle physics which experience all four fundamental interaction, which are in the earlier lecture we have also seen the different kinds of fundamental forces which are there in nature, like electromagnetic, gravitational, strong, and weak interaction. And these are the only particles whose electric charges are not integer multiples of the elementary charge. If you take the mass of any other elementary charge, like you take, if you take the mass of proton, if you take the mass of neutron, it is integer multiple of that of mass of electron. But when we come to quark, they have a charge of the order of 1 by 3e, 2 by 3e, that way. So types of quarks. Now when we talk about different types of quarks, we don't say types of quarks, we generally say different flavor of quark. So there are six flavors of quark: up, down, charm, strange, top, and bottom. Now up and down quarks, they have the lowest mass of all quarks and the heavier quarks. Like if you talk about charm, strange, top, and bottom, they undergo a process which is called as particle decay. And through particle decay, these quarks they form up and down quark. So because of this, up and down quarks are generally stable, the most common in the universe, whereas strange, charm, bottom, and top quarks, they can only be produced in the energy collision, like when we talk about the cosmic radiations there, or in particle accelerators. Now we know that how proton is different from antiproton, how electron is different from positron. They are antiparticles of each other. Similar to that, when we come to the study of quark, which is a sub-elementary particle, in that case also we have an antiparticle of quark which is known as antiquark. Now we know that proton and antiproton, they differ in terms of charge, other properties are same. We know that in case of electron and positron, all the properties are same, but charge is different, opposite. Now in case of antiquark also, what is different, all the properties will be same, they differ in some property. One is electric charge, like as that of the electron and positron, it is equal in magnitude but opposite sign. Now quark model. The quark model was independently proposed by two physicists, Murray Gell-Mann and George Zwick, in 1964. And the evidence for the Quark, it was actually obtained in the Stanford Linear Accelerator Center in 1968. Now, accelerator program experiments have provided evidence for all six flavors, and the top quark, which has more highest mass out of the six quarks, it was first observed at Fermilab in 1995 and was the last to be discovered. So we know that when we try to discover this quarks or these elementary particles, we need amount of energy, and that amount of energy, it is proportional to its mass. So as top quark, it has more mass, naturally the energy required, or the particle accelerator which will be required for detection of top quark, it should have a very high, huge amount of energy. Now, let's come to standard model. So, what is standard model? The standard model is the theoretical framework describing all the known elementary particles. So, in case of elementary standard model, we have six flavors of quarks, like up quark, down quark, strange, charm, bottom, and top. And the symbol for this quarks, it is like for up quark, the symbol is U. For down quark, the symbol is D. For strange, it is S. Charm, it is C. Bottom, it is B. And top, it is T. What are antiquarks? So antiparticles of quarks are called as antiquarks and are denoted by a bar over the symbol. So like if I'm talking about up quark, so its antiquark will be U bar. If I talk about top quark, then antiparticle or antiquark of T, it will be T bar, that way. Now here, as we talk about the antimatter like electron and positron, that they have all the properties same, they differ in terms of charge. In case of antiquarks, they have the same mass, mean lifetime, spin, everything is same, but they differ in term of electric charge and other charges. So in case of quarks, there is a electric charge like we have in case of electron and positron, and also there is one more charge which is called as color charge. So there is a color associated with the quarks like red, blue, and green, and for antiquarks it will be anti-red, anti-blue, anti-green, that way. Now properties of quarks. So quarks are spin half particles. Spin half, that means they are fermions according to spin statistics theorem, and they are subjected to Pauli's exclusion principle, and that means that no two identical fermions can simultaneously occupy the same quantum state. So that means two quarks, they cannot occupy the same quantum state here in case of particle physics. Quarks possess color charge, and that color charge, it is responsible to engage them in the strong interaction, and the resulting attraction between different quarks causes the formation of composite particles known as hadrons. For example, when two up and one down quark, they combine, then you get a proton, so UUD. Now in case of a standard model, we have a generation of quarks. So first generation, second generation, third generation. So I'll show you that this is the standard model of elementary particle. This first column, it is first generation, second column, it corresponds to second generation, and third column, it corresponds to third generation of elementary particles. Each generation, you can see here, it consists of two quarks. Now here in first generation, I have up and down quark, and it consists of two leptons, so electron and electron neutrino. Second generation, I have two quarks, charm and strange, and two leptons, that is muon and muon neutrino. In case of third generation, I have two quarks, top and bottom, and I have two leptons, tau and tau neutrino, that way. So the first generation includes up and down quarks, second strange and charm quarks, and third bottom and top quarks. And all searches for a fourth generation of quarks and other elementary fermions have failed. So we have only, right, as of now, we have only 3 generations. And there is no strong indirect evidence that more than 3 generations can exist and all. Now let's come to properties of quarks. So electric charge. Quarks have fractional electric charge values, either -1 by 3e or 2 by 3 times e. So depending on its flavors. So up quark, charm quark and top quarks. They have a charge of plus 2 by 3e. Down quark, strange quark and bottom quark, they have a charge of minus 1 by 3e. Now if I will talk about anti-quark of up, anti-quark of charm and anti-quark of top, they will have a charge opposite. That means they will have a charge minus 2 by 3e. Down, anti-down, anti-strange, anti-bottom, anti-quark of this down, strange and bottom, they will have a charge opposite, that is plus 1 by 3e. Now let us come to spin. So spin, it is an intrinsic property of elementary particles, and as we have discussed earlier, quarks are spin half particles, they are fermions. Now weak interaction. So a quark of one flavor can transform into a quark of another flavor only through the weak interaction. Now we have studied four types of interaction: strong, gravitational, electromagnetic, weak. But using only weak interaction, a quark of one flavor can transform into another flavor. Now there is an intermediate particle which we call as W boson. So by absorbing or emitting a W boson, any up-type quark, up-type quarks are like up, charm and top. They are called as up-type quarks. So these quarks can change into down-type quark, like down, strange and bottom. They are called as down-type quark. And vice versa. That means if up quark, charm quark and top quark, it absorbs W boson, it will change into down, strange and bottom. And if down, strange and bottom, if they absorb, then we will get up, charm and top quark that way. So this flavor transformation mechanism causes the radioactive process of beta decay. So we know that in beta decay process, what happens? Neutron, it gets converted into proton, we get electron and antineutrino. Now this is how we write down the beta decay process. It is hadron notation because we are talking in terms of hadron, neutron and proton. Now if we want to talk in terms of quark notation, we know that neutron, it is composed of neutron, it is composed of UDD, proton, it is composed of UUD, electron and antineutrino. So this is the notation in terms of quark. So it is called as quark notation. So basically what is happening here, UDD, we are getting UUD. That means one of the down quark, it is changing into up quark, and that is how the neutron, it is getting converted to proton. Okay. So that's all about the quark model. Thank you. Thanks so much.